Okay, I have started the recording for the session. So, yes. Welcome everyone to the first weekly problem solving and discussion session for the physics of nanoscale devices. My name is Jyoteshwaran. I am a PhD student from the Department of Electronics and Communication Engineering of Indian Institute of Technology, Roorkee. I am a PhD student who's currently working under the supervision of the course instructor, Professor Vishwan Singh Punia, and I have acted as a TA for this course in the past two iterations of this course. So, without further ado, let us begin the session. So, these are the topics that we shall be looking at today. First, we shall see a basic overview of the course where we will try to look at the motivations of why we are studying the topics that we are looking at. Because for the first 3 weeks, there is not going to be much discussion about devices. And in fact, for the first half of the course, we shall not be looking at any formal device constructions or descriptions. So we need to give a reasoning, a rationale as to why we are doing this and why learning these fundamentals are important. So after that, we shall primarily be focused on the basics of quantum mechanics that is required for this course. So this is not like an overall course in quantum mechanics. What we are essentially looking at is the relevant portions to the course. Not relevant, sorry, apologies. Relevant to this course. So in that, the main thing that we need to know is the solution to the Schrodinger equation, and even here, it's mostly the 1D problems, so one-dimensional problems, and then a little bit of understanding about the Heisenberg uncertainty principle. These are two concepts that will be relevant as we move further into the course. And on top of this, not on top of this, after looking at these two concepts, we shall be moving on to the particle in a 1D well. So this is, oops, sorry. Yeah, so this will be an application, an immediate application of the Schrodinger equation that we shall be discussing today. We shall be looking at the solutions and thereby going through some relevant concepts in quantum mechanics. And finally, we shall have a very brief discussion on Bloch's theorem. And this is the starting point for the next week's, like week two's topic, which is the chronic penny or the KP model. So, yes. So first, we are looking at the course overview. So why are we even considering or looking at the concept of nanoscale devices? The primary reason is there is an ever increasing demand for computational power. So this ever increasing demand is what is pointed out by Moore's law, where it is said that there will be an order of magnitude increase in the number of transistors per unit area of the die as a certain time progresses. So it gives a kind of exponential growth trend for the computational power of integrated circuits chips. So this automatically implies that we will need to construct smaller and smaller transistors, and smaller transistors implies shorter channels. The catch here is once we go to the shorter channel limits where the channel length is of the order of nanometers, then we can no longer classically or use the conventional approach that we have for transistors or MOSFETs to analyze the properties of such devices. In fact, so even modern day like industry technologies such as FinFET and oops, yeah, the ENT should also be capitalized. and there are also some double, or essentially FinFET is also a multi-gate device, but there are other double multi-gate uh, multi-gate transistors which already have channels that are, of the order of 7 to, I don't have to say, essentially of the order of 5 nanometers. So, it's 5 nanometers or 7 nanometers or thereabout. So, this is the channel length. Apologies once again. Yeah, channel length. So this is not the idea, the notion of nanoscale devices is not some esoteric concept that we are looking at. It is not some future concept that we are looking at, but it is, and it's not even an emerging technology, it is already an industry standard. We have already hit the nanometer regime. In fact, we are going to the point where the channel may contain only a single atom in it, or maybe something even beyond that. We might even transition to a different device structure altogether. So the point is that we are already in this nanometer regime. So it is important to understand the theories that we need to learn to analyze such devices. So the key aim of this course is to convey the idea of this meso slash microscopic conduction theory. This is known as you shall see going down. So this is the Landauer's theory of conduction. So that is the theory that we shall be looking at. Of course, this is not the only method that we may use, but this is the one that we shall be looking at in this course. And this course will follow what is called the bottom-up approach. Essentially, first we will start discussing the fundamental properties of the charge carriers themselves. So we will learn the dynamics of the charge carrier and then introduce the charge carrier into a system, which will be our device, the channel, and then try to understand the actual behavior of the device. So the bottom-up approach implies we start from the electrons and then we go to the devices. Okay, so typically in an electronics course, we will be taught the properties of a transistor, like the input-output characteristic, the transfer characteristic, and all the other things before. I mean, even without teaching the theories of conduction, it is usually not necessary. One can just give an effective model for the transistor and use conventional capacitor and effective capacitance and resistance models to model the behavior of a conventional classical long channel transistor. Such a representation is no longer possible when we are looking at the short channel devices. And as a result of that, we kind of need to move to the bottom up approach, where we start from the physics of the device and then move to the property of the device itself. And since we are starting from the properties of electrons, it becomes essential to understand the quantum mechanical effects and also have, and to do that we need to have a basic introduction in quantum mechanics, which brings us to the first proper topic of, so that is why we are looking at quantum mechanics. And that brings us to the first topic of the day, which is the Schrödinger wave equation. So the Schrödinger wave equation is the equation that is used to give the dynamics. So essentially, what does the Schrödinger equation do? In general, this describes the dynamics of non-relativistic, oh, once again, relativistic quantum systems. So since we are saying non-relativistic, it means that the average velocities or speed of the electrons are going to be very less. And in that limit, the Schrödinger wave equation is one of the tools that we have to understand the dynamics of such a quantum system. So the 1D Schrodinger equation, essentially we are restricting to systems that are defined only in one dimension. The one-dimensional Schrodinger wave equation is given as follows. So we have minus h bar squared by 2m, where h bar is the reduced Planck constant. So I will write that here just for a reference. So this is the reduced Planck constant. And so m is the mass of the particle. So this is the Schrodinger wave equation for a single particle. This, of course, can be generalized to multi-particle systems, but however, right now we are sticking to the simplest possible system where I have one particle moving in one dimension. Um, and then the second term is plus V of x, which is the potential in which the particle is. So V of x is the potential or the potential energy. And V of x times psi of x is equal to E times psi of x. And E is the total energy of the particle. Energy of the particle. So this quantity psi of x, so these are the different terms. The mathematically minded listeners and attendees will be inclined to ask that why am I using the partial derivative here? Since I have explicitly mentioned that this is a 1D system, this term is technically, not technically, if I were to be technically correct, I should have written this as the proper derivative, the entire derivative of this. Or, alternatively, I should have written this as psi double prime of x. However, I have written this as a partial derivative here because in addition to this, even in a 1D system, we can have time dependence, although I have not mentioned it here. And this equation is I should have mentioned this here. So this is the time independent form of the Schrodinger equation. There is also a time dependent form, but we shall not be needing that. The time independent form is all that we need. Independent form. So essentially this form of the equation is used to describe states that have a constant energy, that have an energy that does not vary with time. So E additionally is also a constant. And again, people who've had some, math training will know that this equation is in the form of an eigenvalue equation. So this equation here is an I can say that this is where do I write it? Yeah, I'll just put it down here. So this whole equation is an eigenvalue equation. So what are eigenvalue equations? So eigenvalue equations are equations of the form where I have d f of x is equal to some k or using lambda f of x. Equations of this form where d is some differential operator or in general any operator, and lambda is a constant. So this is a constant scalar usually. Okay, so the operator D can be a scalar differential operator. It may also be under conditions a vectorial differential operator. But ultimately on the other side, I get the same function f of x multiplied by a constant. So this is of that form where I can say that the differential operator D is this quantity, everything other than psi. It is minus h square by 2m d square by dx squared plus v of x. So this quantity is known as, so here in this case, wow, before beginning the free particle solution, kind of run out of space, no problem. I can use another slide. So for the Schrodinger equation, um, d is this quantity minus h bar squared by 2m. In fact, if I were to write it as in the 3D form, so yeah, I will kind of insert that. So this is going to be the Laplacian here plus v of x comma y comma z. So this is the operator. This is kind of multiplied with psi, and therefore the Schrodinger equation in 3 dimension is going to be d of psi x y z is equal to e of psi x comma y comma z. So this is the general three-dimensional form of the Schrodinger equation, and it is because of this that I wrote the partial derivative, second order partial derivative here. However, since we are only looking at the 1D case, this becomes equivalent to this because the other two position coordinates are irrelevant. So, as mentioned in this slide itself, we shall look at the free particle solution. Let me insert a new slide, make it a blank slide. So now we are looking at the, let me use a different color, yes. So we are looking at the free particle solution. So what are the free particle solutions to, so what does the free particle system mean? It means that V of x is equal to 0. There is no potential, there is no, let me make 0 proper. Yeah, V of x is equal to 0. So this implies the particle has no potential, no restrictions whatsoever, and is free. So in this case, the Schrodinger equation will reduce to minus by 2m d squared by dx squared psi of x is equal to e times psi of x. Now this would imply minus 2m e upon h bar squared psi. I'm just dropping the other symbols for the sake of brevity. So this would imply this equation is of the form psi double prime is equal to minus k squared psi, where k is equal to 2m e by h bar squared whole power half. So this quantity is what we substitute for k. And from this, we know that psi of x, let me try to, apologies once again. Yes, psi of x will have the general form a e to the power I kx plus b e to the power minus I kx. There is a reason I've written it like this. In the lecture slides, you will see that the solution is given as the sine and cosine function. But for my own reasons, I'm choosing to write it like this. One can easily see that since e to the power I kx can be written as cos kx plus I sin kx, it is possible to rearrange these terms and write it as sin kx plus cos kx also. So this is the general free particle solution. So this is the free particle solution for the wave function. So the first thing we can say is the following. I know that the this function is always going to be bounded. Essentially, the absolute value of, so in this, the absolute value, this implies, yes, I can write it like this. Sorry again, yes, psi of x is less than infinity for all x, because e to the power mod e to the power ikx is equal to 1. So since the magnitude of these complex numbers is 1, and oh yeah, okay, so there is one more thing that I should have done here. I cannot, oh yeah, I can do that, yes. So it is less than infinity because ultimately it is only going to depend on the value of a and b, and to assume a and b are infinite would be to assume an improper solution. Whenever we take such a solution, we assume that the values of a and b are finite. So as a result of that, the modulus of the wave function is also finite. And also we can see that since this is e to the power ikx is a combination of sine and cosine functions, another thing that we know is the free particle solution psi of x is also periodic. So what is the periodicity? The so periodicity is periodicity is equal to, so if you can just look at this, e to the power I 2 pi is equal to 1. So I need to make my x go to 2 pi by k times x. So this is a essentially, if I'm looking at the real part of this wave function. So yeah, let me go to another slide. That'll make life easier. Yeah. So if I look at the real part of e to the power ikx, that is nothing but cos kx. So now this is going to be, yeah, this ought to be enough. Yes, so if I were to say this is plus 1, this is minus 1, then if the power ikx is going to vary like this. Yeah, apologies for any shaky figures. Oh my god. I was talking about the cosine function and ended up drawing the sine function. Yes, it's going to be like this. And it will oscillate ad infinitum, like all the way to infinity. Okay, so this is my x-axis, this is my y-axis. So at x equal to 0, this quantity is going to be 1, and it will hit 0 at a certain point, and it will rise up over here, and the full period, yes, let me extend it. Let us say it reaches 1 over here. Yeah. And it's a good thing that I added that line, yes. So this is one full period of the function, and this has to be equal to an angle rotation of 2 pi. So this quantity over here, yeah, let me get rid of this x as well. So yeah, so this quantity here has to be, the argument has to move from, so when x equal to 0, the argument for the cosine function is 0. Whatever the value of x, over here the argument should be 2 pi because it has finished one full period. So here x is going to be 2 pi by k, which would make this the midpoint, pi by k, and this is going to be pi by 2k. So this is the idea, and from this we can see that the full period is 2 pi by k, which implies the wavelength. So lambda, which is the wavelength, is equal to 2 pi by k. Therefore, k is equal to 2 pi by lambda, and k is known as the wave number. This is something that people may know from their electromagnetics courses, or even from their school days when they learned electricity and magnetism. So this is that. So if we can go back and look at the value of k and kind of multiply by 2 pi, we can see that k is equal to, or rather I can say lambda will be equal to h divided, because h bar into 2 pi is going to be h square root of 2me. So this, since I am in the non-relativistic regime, and since V is equal to 0, potential is 0, I can say that E is equal to P squared by 2m, which is the kinetic energy. Only the kinetic energy is here. This will further imply that lambda is equal to, therefore 2me square root is going to be P h by P, and this is what we call the de Broglie wavelength. Yeah, some people may call it the de Broglie wavelength. Yeah, de Broglie is the pronunciation of the name. So this is the de Broglie wavelength. This is also something we will be using down the line. So now we have taken the idea of a free particle. We have seen a couple of things, properties of this free particle solution, and from that we have also derived the quantity of a wave number and the wavelength, and these are things that may become relevant, not may, will become relevant down the line. Okay, so now let us look at some general properties of psi of x. So general properties of psi of x. So first and foremost, the quantity psi of x is finite. It has to be finite valued. It cannot have a value of infinity. Second property is psi of x has to be continuous. Now, why does this have to be continuous? The reason for that comes from this differential equation. So properties of differential equations would require that this quantity, like for the second derivative to be defined at every point, I need my first derivative to be defined at every point. For my first derivative to be defined at every point, I will need my function to be continuous. And there is a second condition which for a 1D system, now all of this I'm writing for a 1D, for multidimensional systems, I need to make suitable generalizations. Another condition that you may have encountered in the lecture is that the derivative should also be continuous. Now this is not always true. This is true in most cases, but one should remember that this is not always required. There are some nice counterexample. They may not always be physically relevant or physically realizable systems, but they may very well be relevant examples. So we will look at one case where this condition is dropped, in the next problem solving session. The next important property is this. And this is the most important property. Ooh, apologies, too many brackets. Yeah. Oh, yes. Another thing that should be mentioned here is this is finite, and in general, as seen right here, in general, this is a oh, this is a complex valued function. So in general, a wave function will have complex values. It is not a real valued function. So yeah, now this quantity, what is psi squared x? This is the probability density function for the particle. So what does this mean? What this means is the following. It means is if I were to define the quantity probability of particle being found in x to x plus dx is equal to mod of psi of x squared dx. Remember that this quantity itself is not the probability. This is merely a density function. If I need to find the probability of the particle being between 2 points A and B, then I will need to perform the integral. So that would be like I will need to integrate this quantity between these limits. So if this is not clear, can I make this slightly smaller? Because I will get some more space. Yeah. Perfect. Yes. So alternatively, probability oops, yeah, particle is in x which belongs to some interval a to b, like 2 points on the x-axis a and b, then that is given by integral a to b. Yeah, too many curves on the side. Yes, dx. This is the probability. Please do not consider psi of x square to be the probability. Okay, so we will see a proper clarification on this when we come to the particle in the 1D box. And finally, since this is a probability distribution, if I were to integrate over all possible values of x, one second. If we were to integrate, yeah, I'm sorry for the interruption. Yeah, if we were to integrate from minus infinity to infinity, then psi of x squared dx is equal to 1. So this condition is the normalization condition. So now if looking at this, one may be inclined to go back and ask, can this function be normalized? The answer to that is actually no, because the integral of this function is not like it diverges. But as a counterpoint, what I will say is this situation where there is no potential anywhere, in a 1D system, that means the particle is completely free. Means there is only the particle in the universe and nothing else. So this is a very ideal situation. So this is not going to be realizable under any circumstance because we already exist in this universe. So if I want to look at a universe where there is only one particle and nothing else, then by definition I will have to remove myself from that universe, and that kind of closes the door out on me. So this is a very ideal situation. In fact, I shouldn't even say this is a very ideal situation. This is essentially a toy example and not physically, you know, not physically realizable. Oops. Realized. Yes. So we will soon move to another more relevant example, which is actually even at least in an approximate sense physically realizable. Okay. So, but even before looking at that, let us consider a second case where I have the finite potential solution. So what is the finite potential case? I am assuming V of x is equal to some quantity V naught everywhere in space. So I have a finite potential value everywhere in a one-dimensional space. So then what happens to my Schrodinger equation? I will initially start with this situation. Oh yeah, not to forget, plus V naught psi of x equal to E psi of x. This is the equation I need to solve. So immediately we can see that, like, I will make all the like if we make all the necessary transpositions and multiply by appropriate constants, what we will be left with is this second derivative of psi of x. Uh, Apologies. Give me just 1 second. Yeah. Yes. So the second derivative is going to be as follows: minus 2m by h bar squared into e minus v naught times psi of x. Now again, one will be tempted to look at the case of the free particle solution and say that my constant k, so this is also of the form psi double prime of x is equal to minus k squared psi of x. So I would be tempted to say that k is equal to square root of 2m e naught minus b by just 1 second. My square root was not deep enough or tall enough. Yes. Yeah. So this quantity, and then I can say I can go ahead and solve it. But remember, we have not decided on the value of E. So E minus V naught may be positive, may be negative. So let us look at both those cases. So first case is E is greater than V naught. In that case, K is positive and So not positive, k is real, implies k is real, and that implies the solution is going to be, you know what, I will not call this k, just to distinguish from the free particle solution. Let me say that this is of the form alpha squared, and I will say alpha is alpha is equal to this. So yeah, then I'll have to change it to alpha here also. Yeah, now we are good. So alpha is real, and therefore psi of x for this psi of x for this case is going to be a e to the power iota alpha x plus b e to the power minus iota alpha x. Now, this seems to be a very good ideal case. However, what we need to look at is the following. What happens if E is less than V naught? In that case, what will happen is alpha is going to be imaginary. In fact, alpha is going to be purely imaginary. What does purely imaginary mean? Essentially, what happens here is this quantity here, if E is less than V naught, this becomes negative. So I am taking the square root of a negative number. The square root of a negative number is the square root of the magnitude of that number into square root of -1, which is the imaginary number iota. So this further implies alpha is equal to iota times lambda, where lambda is equal to mod of the magnitude of 2m e minus v naught by divided by h bar squared whole power half. This bracket implies I'm taking the absolute value of the quantity. Okay. So now what will happen is, of course, the solution is going to look exactly the same. I just have to plug in the value of alpha. But alpha is now a purely imaginary quantity. Therefore, psi of x is going to be a e to the power minus lambda x plus b e to the power lambda x. If I just substitute iota times lambda, iota squared is -1, and minus iota squared of course is 1. So this is the form of the solution that I'm left with, and this is a real quantity. Please remember that. So this is a real number. So now this seems to be the solution. Now where does this leave us? First question, is this a continuous function? Uh, Of course, it is like the exponential function. We know it is a continuous function. The derivative is everywhere defined. Uh, in fact, it is infinitely like I can take any order derivative and all of them are well defined. However, the first condition is what that comes into trouble. Remember that psi of x above all is a finite valued function. Now, this quantity tends to infinity at 2 points. Now, in this case, this quantity has two divergences. Psi of x, so let me say this is equation 1 or solution 1 and this is solution 2. Psi of x in 2 has two divergences. Oops. Divergences. Namely, at x tending to plus or minus infinity. When x tends to infinity, this quantity becomes infinite. When x tends to minus infinity, this quantity becomes infinite. So now what do we do? What we will have to do is the following. Now that means A and B cannot have a constant value for all x. So what we need to do is when x greater than 0. So when x greater than 0, I need to keep my wave function finite valued, which implies I will need to choose one of these functions where the wave function is finite, and that is e to the power minus lambda x. Therefore, I will have to say b has to be equal to 0. And when x is less than 0, by similar reasoning, I have to say a is 0. So I'm having a situation where x is e to the power minus lambda x on one side and e to the power plus lambda x on the other side. It is e to the power minus lambda x when x is greater than 0 and e to the power minus lambda x, sorry, e to the power lambda x when x is less than 0. So how do I try to combine this and write this as one solution? So how we do that is to realize what happens at x equal to 0. Remember, when x becomes fully less than 0, I only take one of these two functions. When x becomes fully greater than 0, I only take one of these two functions. What do I do at x equal to 0? To answer that question, we will have to look at the second condition. Psi of x has to be continuous. So whatever the value it is as limit x tends to 0 from the positive side, and whatever value it is as limit x tends to 0 from the negative side, both has to match. So by looking at that condition, essentially limit x tending to 0 plus, which is when I'm tending to x from the positive side, psi of x has to be equal to limit x, oops, x tending to 0 minus psi of x. So over here, this implied we had a piecewise solution. So, okay, let me once again do something. Yeah, all of these can be moved over here. Yes. So let me write the solution to the wave function all the way over here. So this implies psi of x is equal to a e to the power minus lambda x for x greater than 0, a, sorry, b e to the power lambda x for x less than 0. But now I still don't know what the values of a and b are. But I know that these two limits have to agree. Now we know as x tends to 0, this quantity will tend to 1. Therefore, when I'm looking at it from the right side, this will tend to a, and when I'm looking at it from the left side, it will tend to b. So since these two limits have to be equal, so in fact, I can go back to this slide, select this quantity, and move it to the next slide. So by imposing the continuity condition, so if I say psi of x is continuous, then that implies this, which further implies a should be equal to b. So let me say that quantity is a itself. So then I can go back and see this a and b have to be equal. Then I can additionally look at how x is changing signs as x becomes negative and x becomes positive, and say that The general solution psi of x takes this form, which implies psi of x is equal to a e to the power minus lambda mod x. So when x is less than 0, mod x will, oh wait, oh no, in this form where I've written it, oh yes, of course, then I don't have to write the minus here. I can get rid of the minus, yes, because when x is less than 0, mod x will make x minus x. When x is greater than 0, mod x is x. Essentially what I'm saying is, if I'm looking at the definition of mod x, the mod function, this is equal to x for x greater than 0 and wait, oh no, then I have to do minus, yes. Apologies for the confusion. Yeah, I got confused by the signs, yes. And minus x for x less than 0. So this is the mod function. So looking at this, I can say that when x is greater than 0, it will be x here, and I will be using the function e to the power minus lambda x, which decays to 0. And when x is negative, I will be using e to the power x, which will make sure that as x tends to minus infinity, I will tend to 0 over there as well. So yeah, yes. So this is the solution. Now let us quickly look at the graph of this function. So I will just, make an approximate sketch of this. And we see that now for this potential, the solution is over here. This was a periodic solution. So when E was greater than V naught, I got a periodic solution. But when E was less than V naught, we did not get a periodic solution. This function is clearly not periodic. So graph is going to be something like this. On this side, it is e to the power minus x, so it's kind of like decaying. And similarly, on this side, it is going to decay. And decays are symmetric, so please don't think that it is decaying faster on one side. Like this is just due to the poor quality of my drawings. So this is going to be at the point A. This is psi of x. This, of course, is x. And I have the origin 0 over here. So now what does this tell me? This tells me two things. First, since this is tending to 0, this implies limit, you know what, I'll write it in green. So this figure clearly shows us that limit x tending to plus or minus infinity of this quantity, which is the probability density function, is also 0, because that is just the square of this function. In fact, it will, if I take the square of this function, it will decay even faster. So that tells me something very important. This tells me that the probability density actually vanishes as I am moving farther and farther away from the origin. This means the probability, so this further implies the probability of finding, because whatever integral I may take in any interval away from the origin, it will become smaller and smaller the further and further I move away from the origin. Okay, so oops, where was I? Yeah, here. Particle very far, not even very far, I can just say far. away from the origin is tending to zero. Okay, so it becomes vanishingly small, which implies the probability of finding the particle close to the origin is that much high. So, as a corollary, so this implies uh, probability of particle being near origin is high. This is what is referred to in quantum mechanics as confinement. So, a particle is said to be confined in a region if the probability of, so confined, this is what we are trying to define, of finding the particle outside of that region is vanishingly small. Yeah, before I proceed any further, there is a way to determine what the value of a in this function is. To do that, all we need to do is look at this last condition, the condition of normalization. So what I will recommend is all of you try to find the value of a, capital A, and then you can also, uh, so yeah, before we proceed any further, let me see if I can switch to a different color. Yeah, so this is a homework from my side. Of course, I have no means of verifying this, so please do this or don't at your own discretion. So for the solution from equation 2, first find the value of a, and second, and find the region, uh, or yes, x, such that, find the region, find the interval mm, minus, what shall we call, what is a good symbol, minus L to L, yes, minus L to plus L, such that integral minus L to L mod psi of x whole squared dx is equal to 0.99. Essentially, what I'm asking is find the point minus L and L on this graph such that the probability of finding the electron inside that boundary is 99%. Okay, that is essentially what is asked. So the form of the function is given here. You can do the normalization and find A, and then you can again repeat the same exercise and find the value for L as well. So this is a small homework exercise I'm giving. If you have any difficulties, you can post this question on the forum for the course, or alternatively, you can join me next week and ask the question. Then I will be able to quickly solve this in the next week's problem session. I'm giving this as a homework. I'm not working it out here, so that you also have something to think about in the off time. Okay, so yeah, this is the definition of confinement. Okay, and another thing about a few words about confinement. Now, why I'm talking about confinement is so confinement in quantum mechanics. So, so what is so special about confinement in quantum mechanics? So, first thing, most physically realizable states are confined, and this makes logical sense. Like if I'm looking at the state of an electron present in the channel of a device, then of course I'm assuming that the electron is bound inside the device. So, in that sense, I'm looking at a confined state. And any non-confined state has to be something like, oh no, apologies, something like this. And we know that this is never physically realized. So we have already like kind of seen that. So most physical, in fact, why most? All physically realizable states. Yeah, I don't know why I said most here. So all physically realizable states are confined state. Secondly, any confined quantum particle will have quantized energies. Okay. So this is will be commonly referred to further in the course as confinement implies quantization. So this is something that needs to be understood. So typically, if I'm looking at a realistic wave function like this, then it will also automatically imply that the values, allowed values of E for this case is not going to be infinite. There are, I mean, it may be infinite, but it is not going to be continuous. Only discrete values of E will be possible. So now, why is that? We will see in a few more minutes. But before we look at that, let us look at the next concept of today's discussion, which is the uncertainty principle. So the uncertainty principle is was originally formally introduced into quantum mechanics by Werner Heisenberg. So they are also referred to as the Heisenberg uncertainty principle. There are many formulations of the relation. The ones that we shall be using in this course are of this form. Like other textbooks, you might find alternatively on the right hand side, you might find quantities like h bar by 2, or which is equal to h by 4 pi, or some sources will simply even write this as h. So, there are multiple ways to write, but this is the form that we shall be considering in our course. We are not going to look at any further, versions. This is the one that we use. There are reasons why we choose these different values, but, you know, For all, like for convenience, we can choose this. Like we don't have to get too much into the technicalities. Again, if you have any questions regarding this, you can post on the forum, and maybe I will try to answer that separately. A discussion about what to have on the right hand side of my Heisenberg uncertainty relations is not within the purview of this course, and I don't think we need to spend too much time on that either. So now, what does the uncertainty principle mean? What is the message that it conveys? So we have I have given two uncertainty relations over here: position momentum and the energy time uncertainty relation. So what does this mean? So the essential point here is that the position and momentum can never simultaneously have a constant. I shouldn't even say constant, a fixed value. So that is what this statement conveys. The uncertainty represents the error. Now, this error is usually represented as the standard deviation of a certain distribution. And since I know that the value of these two uncertainties is always a positive non-zero number, is at least a positive, this number over here, then I know that either of these quantities can never be zero, because if one of them becomes zero, the other will tend to infinity automatically. So this means that whenever I'm considering position and momentum, yeah, I should have elaborated slightly more of a quantum particle. Quantum particle can never simultaneously have a fixed value. In fact, a stronger statement here, if you followed my previous description, is neither one of these quantities can ever be zero with the risk of the other diverging to infinity. Therefore, in a physically, okay, I will come to that in a minute. Yeah, you can scratch that. We can restart from this statement again. And just for the purposes of neatness, I will write, yeah, H bar again. Yes. Okay. So, and this doesn't look like a H. Apologies. Yes. So, yeah, where were we? So what does this mean? So this means that there is always going to be error in the position and the momentum. So does this mean that whenever we try to measure the position or momentum of a particle, we will end up making errors? The answer is actually not that. This is not the error that the observer or the measurement device makes. This is not saying that I can never make a device that will make accurate measurements. This is a physical relation. Now, what do I mean? So, what I mean is the following. Let us say I am using some device. I don't know what it is. I'm using some kind of a machine. And, confining. So, let us consider a, what? I will use the language of the people who founded quantum mechanics, and let us, I will try to write this. So, yeah, assume assume that we are trying to catch a quantum particle. So what are quantum particles? Well, technically, every particle is a quantum particle, but we can come to that later. When I say quantum particle here, I mean things like electrons, atoms, even electrons, atoms, etc. Let's not again get too much into the details. So let us say we are trying to catch it. So by catching, what am I trying to do? I'm trying to hold it in a place. Okay, so let me say I'm kind of trying using some kind of a box. Yes, now we are coming to the situation. So let us say I'm trying to put a single atom inside a. Let us say I'm trying to put let us say it's an atom. Let us say I'm putting an atom, not. Let us say I'm trying to put an atom in a box, and the thing on the outside is a box. Okay, so what the uncertainty relation implies is this. Now, when I put it into a box, what have I done? The atom is now confined. So this implies the atom, or yeah, the atom is confined. Now, remember what I mentioned before, confinement implies quantization. So I can say that, yes, now that it is confined, its energy is going to become quantized. But what the uncertainty principle says is this. Now, delta x. Now, again, I have given an example where I'm considering a two-dimensional box because that is easier to imagine. But you can also imagine a 1D box, as we are going to see in a few more minutes. We will like uh, have a mathematical representation for a 1D box. It's not possible to draw a 1D box. Uh, it's not possible to draw it. So that's why I've drawn a 2D box. Now delta x is a measure of the size of the box. Okay. So what this relation is telling me is that the smaller I try to make my box, the smaller the value of delta x will become. Now, by the uncertainty relation, this implies delta p is greater than or equal to h bar by delta x. Therefore, the smaller I try to make the box, the larger the uncertainty in the momentum will be. Now, what implication does that have? The implication is as follows. The implication is as follows. When I say delta p is greater than or equal to h bar by delta x, this implies a decrease. Of course, this is an inverse proportionality relation. That means delta x implies an increase. No, I should use two implications. Leads to an increase in delta p. Now, what I'm going to say is something like this. Let us say initially the atom had very low momentum. Let us say it was a very slow atom around which I built a box and I'm trying to close in. If initially, okay, so let me write that separately here. So also, if initially, no, what am I? Yes, initially P was very small, Then upon confinement, I can say P is approximately equal to delta P, because as delta X becomes smaller and smaller and smaller, this quantity delta P is going to become larger and larger and larger. So I can say whatever my momentum is, it is supplied entirely through the uncertainty. That implies the energy of the particle. Let me also assume there is no potential inside this box. So let me say inside this box V is equal to 0. Okay. Then, yeah. E non-relativistic case is equal to delta P whole squared upon 2m. So what does this mean? This means that the smaller and smaller I am trying to confine my atom or my quantum particle in a smaller space, the more energy it will tend to have. Now, does this, the act of, essentially what I'm trying to say is the act of confinement is somehow giving energy to the particle that I'm trying to confine. So, what does this mean? Like, can we see a realistic example for this? The answer is yes. So, the answer comes from the following. Say, take a solid object, any solid object. Like, likely most of you are, sitting in front of a table and, or you're at least sitting on a chair or, lying down on a bed and watching this on, some kind of a device. You're either watching it on a phone or a laptop or, a desktop display. And what I'm trying to say is you are in contact with a solid object, or at the very least, you're sitting on the floor. I would like to ask you the following question. So, when we are sitting on a solid floor, why is the floor able to support our weight? What I'm trying to ask essentially is when I apply a certain force to a solid object, it seems to be able to apply a reaction force. Like this is something we know from Newton's third law. So why is there an equal and opposite reaction coming from the object? Like how is that possible? Like where is that energy coming from? So that energy is essentially like that's a reaction force. That is, I mean, if we are talking in Newtonian mechanics, it just says that whatever force I'm applying, I'm kind of receiving a normal reaction or some kind of a reaction force to that. But how is that force kind of being reversed at us? Heisenberg's uncertainty principle gives us the answer. Essentially, when we are pushing on the table, what we are trying to do is we are pressing on the atoms that the table is made of. That is effectively trying to compress the solid. So when I'm trying to compress a solid, it will tend to push back. And this pushback is essentially what is felt as a normal reaction. And that pushback is due to this extra momentum or extra energy it gains as I'm compressing it. And that is a direct consequence of the Heisenberg uncertainty principle. So even something that we have known for a long time, like a reaction force is fundamentally related to the quantum mechanical nature of matter. Now, that kind of confinement is not present on a liquid body. So when I try to compress a liquid, they are more easily compressible, and I can, in fact, it is also penetrable. Essentially, I can throw something into a liquid on a liquid surface, and it will move through the liquid. But a solid object is impenetrable. Like I cannot move through a solid. The only way I'm moving through a solid is by breaking it. So I will have to supply so much energy that the material itself breaks, and only then can I pass through it. Otherwise, for whatever force I'm applying, I'm going to get a reaction. And that reaction is fundamentally due to the atomic nature of solid. And it is also for this very reason that a true description of solid structure was not possible unless until the advent of quantum mechanics. Like people knew what solids were, there were many studies done, people knew what crystals were, crystal structure was studied, but how do a bunch of atoms form a crystal? this question was not answered until quantum mechanics was, developed. And in fact, it is one of the first prominent applications for describing the properties of solids. For proper application of quantum mechanics was describing the various properties of solids. So the very fact that matter can exist in a solid phase, and if we were to go into further depths, the very fact that matter can exist in any phase is in one way or another a quantum mechanical effect of some kind. And the notion of Heisenberg uncertainty principle is very strongly present in the case of solids. So now let us see. Before that, let us also look at the second uncertainty relation. I will not talk too much about this. The I will just put a comment on this slide saying will be important in subsequent weeks, later weeks. Since this is something that we will be explicitly using in the syllabus, I have written it in the slides. We may not be using this too much in the syllabus, but we will be solving a problem in this very soon. What I will say is when this quantity becomes relevant, I will come back to this and discuss this. Okay, but similarly, there if I have an uncertainty in the energy of the system and the one second and the time, by time I mean the lifetime of the system, then they also have a similar uncertainty relation. So yes, so that is what I will leave the energy time uncertainty relation like this for now. This relation here is up here only for the purposes of your reference. And whatever we discussed here, I will just briefly summarize so that. And you can ask now for people wondering how the act of confinement itself leads to transfers energy to the particle. Well, to confine something, I need to set up some kind of a barrier. Oh, you know what? I will talk about it when we go to the problem over there. Let's put a pin on that. So let me add a third point. So first, I said confinement implies quantization. And smaller the confined space, greater the quantized energy. Okay, so I will just leave it with this comment, and what this means will become much more clearer when we look at the example of a particle in a 1D box. But before moving over to that, let us consider a small toy example. Now we are given that a particle is confined in a 1D space of 5 nanometers. Okay, so estimate the minimum energy that can be possessed by this particle. So how do we go about this? Essentially, we are going to do whatever I described here. So since confinement is in 5 nanometers, I'm going to say delta x is equal to 5 nanometers. And let me say the particle is an electron. So for an electron, m is 9.1 into 10 to the power minus 31 kilograms, which I'm approximating as 10 to the power minus 30. Okay, so I know delta x is this, which is 5 into 10. Like I'm also writing them in the corresponding standard units, SI units. Okay, so now I know delta p is greater than or equal to, h bar by delta M. Now H bar, just yeah, whatever. Yes. So H bar is H by 2 pi, and I know H is 6.62 10 to the power minus 34, and the denominator is also 6.28 or something. So you know what? I'm just going to say this is approximately 10 to the power minus 34. I'm being very loose here, so it's fine. So what does that imply? That implies delta P. Oh no, what is delta M? There is no delta M. I'm really sorry. Yeah. Delta X. Apologies for that error. Yeah. So is greater than or equal to 10 to the power minus 34 divided by 5 into 10 to the power minus 9, which is equal to 2 into 10 to the power minus how much is that? That's 10 to the power minus 25 by 5, 10 to the power minus 24. So, yeah, wait. No, 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 no. 10 to the power minus 26, I suppose. This is 10 into 10 to the power minus 35, yes. Apologies. 26. So, this is the value of delta P. Now, this would further imply E min, or rather I can say E is greater than or equal to this quantity delta P squared by 2m. So this is going to be 4 into 10 to the power minus 52 divided by 2 into 10 to the power minus 30, which will come out to be 2 into 10 to the power minus 22. Now this may not look like much, and this is in joules, but joules are a very large unit of energy. Like, to talk about joule, like 1 joule of energy transfer, I will have to talk about something like heating a few grams of water. And a few grams of water has an enormous number of atoms, like to the order of 10 to the power 23 atoms present in it. Therefore, a more relevant unit is going to be, so this is approximately 10 to the power minus 3 electron volts. 1 eV is equal to 1.6 into 10 to the power minus 19 joules. So if I look at it in the electron volt scale, this is to the order of 1 milli electron volt, which is actually not that small. Like, this is, in atomic scales, a milli electron volt is, of course, it is small, because in atomic scale, the electron volt is kind of the base level. But this is not completely non-trivial. This is definitely a non-zero value of energy. It means that at least 1 milli electron volt of energy should be possessed by an electron that is confined in a 1D space of 5 nanometers. So this is kind of a soft estimate that we have. Let us see how this translates into an actual example. So now we come to what is called the 1D problem of the particle in a 1D potential well. It is also referred to as a 1D infinite well, or alternatively a 1D square well. Do not ask me what a 1D square is. A 1D square is essentially just a straight line of any length. So, but the square here, I don't think it refers to that. I think it refers to the potential profile, which looks as follows. Oh, sorry. So, what does this function definition correspond to? So, it means I have Even with grids on the slides, I struggle to draw a straight line. Yeah, so this is v of x over here, and this is the origin. And let me say this point is when x is equal to a, this is the x-axis. So, yeah, what this means is there is a barrier here at x equal to 0 and a barrier here at x equal to a, and I define three regions where here b is infinite, v is infinite, and in the middle v is equal to 0. So this is one way of defining a one-dimensional confinement. So when I was talking about a confinement in 1D space, I was talking about some kind of a potential like this. Now, why is this confinement? Yeah, I shouldn't have mentioned confinement here, but let us see how this is a confined state. So essentially, this is the potential, and we are going to try to solve the uh, ground state energy of a particle in the above potential. And we are going to compare this to the estimate that we made. The estimate being 1 millielectron volt. Okay, so again, that's all. It's a very soft approximate value, but let us see how well it holds up. So now to solve this, I need to look at the Schrodinger equation. The Schrodinger equation is again minus h bar squared by 2m. Now I'm going to just use the shorthand notation as we are moving towards the end of the session, plus v of x psi of x, and let me say for reference, this is region 1, region 2, and region 3. Okay, so negative x, x greater than a, and x between 0 and a equals e times psi of x. Now, in regions 1 and 3, since v is equal to infinity, the differential equation is poorly defined. Or rather, the differential, I shouldn't say the differential equation is poorly defined. Differential equation has no proper solutions. Why? Let us just go back here and look at this quantity. Uh, look at this point here. See, the value of v here is given to be infinite. So no matter what value I choose here, I'm going to be ending up with a minus infinity. And once I have a minus infinity, like square root of infinity is also going to be infinity. So this thing is, going to be e to the power minus infinity times x, and if you actually take the limit of that, you'll get a function that immediately falls to 0. So this is not a properly defined function, and the only solution I can have for such a function is psi of x is equal to 0, which implies, no. Therefore, psi of x equal to 0 is the only allowed solution. So over here, let me write that psi is equal to 0 and psi is equal to 0. You can just look at this equation. Like if I have v tends to infinity, and the only way I'm going to like have a finite quantity in this, like make all quantities finite in this differential equation is by setting psi of x is equal to 0. Once psi of x becomes 0 here, it will multiply with v of x to kind of like I will say that infinity times 0 is 0, but the 0 function second derivative is also 0, and e times like any number times the 0 function is also 0. So the equation is going to become 0 on the left and right sides, and that is the only thing I can do here. So 1 and 3, psi of x is 0. Now what about region 2? So into the equation again reduces to our well-known. Okay. Psi of x is equal to minus 2 me by h bar squared psi of x. So this is kind of why I spent almost 40 minutes in the Schrodinger equation solution, so that I didn't have to go through it here. Now let us try to derive the wave function using our initial solution rather than the sine and cosine forms. Okay, so I know psi is equal to e to the power I k a e to the power I k x plus b e to the power minus I k x. So first things first, psi of 0 has to be 0. Now why am I saying this? Because for all values of x less than 0, psi is 0. And going all the way back to our initial slides, psi of x has to be finite, and 0 is a finite value, so we also managed to satisfy that. And second, psi has to be continuous. So for it to be continuous, of course psi of 0 has to be 0. Now this automatically implies a is equal to minus b, because at x equal to 0 this quantity becomes 1, this quantity becomes 1, so a plus b is equal to 0. You know what, for the sake of completeness I will write that, just so people don't get confused, which no, therefore a is equal to minus b. Now since a is equal to minus b or b is equal to minus a, I can write psi is equal to a e to the power ikx minus e to the power minus ikx. Now this I can directly write as this implies psi of x is equal to 2 iota times, yeah, a into sine kx. Okay, so yeah, now our second condition is if it has to be continuous at this point, it also has to be continuous at a. So let me just make a new slide. Second condition is psi of a should also be 0, which implies 2 iota a sine ka, looks like sine lk, ka is equal to 0. From this, I can say k times a should be equal to n times pi, where n is equal to 1, 2, 3, so on and so forth. Because if I set n equal to 0, then this will become sine 0 and it will become the constant 0 function. That would imply the particle is present nowhere because the probability density will become 0. But I know there is a single particle in the 1D well. So 0 is not an acceptable solution. Okay. Although it will satisfy the continuity and all those things, ultimately I need to remember that it is some mod psi square should represent the probability density of a wave function. Okay. So I will write above here n equal to 0 implies no particle. Just again for the sake of completion. So this is not consistent. Okay. Yeah. All right. Or To write a compact notation, n belongs to z plus. It is a positive integer, or I could have said n is a natural number equivalently. Okay, so I know this, therefore this implies, oh yeah, here I can say k is equal to n pi by a. Therefore, psi of x is equal to 2i by a into sine n pi x upon a, which is the width of the well. Now, how do I find the value of a? We use the normalization condition, and that exercise is not going to change. In fact, if I take the modulus squared of this, you will see that the iota kind of vanishes, and after doing everything, what we will have is, or rather I will say upon normalization. Now I'm not going to repeat that because that has been done in the lectures. Yeah, sorry. Normalization, I will have psi of x equals square root of 2 upon a times sine n pi x by a, where, just to reiterate, n is equal to 1, 2, 3, and so on. Okay, now how do I find the first energy value? Now I know k is equal to 2m e upon h bar squared, or rather I can say k squared is equal to this, which implies e is equal to h bar squared k squared upon 2m. From this, eagle-eyed observers can see that since E is also equal to P squared by 2m, oops, by 2m, I can quickly by analogy say that P is equal to H bar K, which is a general result. However, remember, I cannot get the exact value of the momentum for this wave function through this expression. If I'm given a wave function with a k value, and mind you, the k value has to be unique, I cannot use this and say what the momentum of the particle here is going to be. Because remember, there are actually two k values here, plus k and minus k. Both waves are present here. So there is k is not single value. Okay, but P is equal to H bar K is a general result, and you can use it in other situations. So from this, I can further write this to be E to be H square, H bar squared, N squared, pi squared upon 2m A squared, which implies ground state energy, which is the minimum energy. This is what is referred to as the ground state, the lowest possible energy. First and foremost, as you can notice, because the electron was forced to be confined in this value, it can never have zero energy. It has a finite positive energy. Now let us see what that is. Pi squared, oops, by 2m A squared. Now you know what? Let us try substituting the values. So this is equal to pi squared upon 2 into h bar squared by m A squared. Yes. Now I actually know what h bar squared by. Oh wait, I actually know. Oh yeah. Let me Oh, no, 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 I need to go further back. Yes. See, I actually know what h bar by A is. Okay. Oh, no, okay. I am getting ahead of myself. Let us say A equal to 5 nanometers and M equal to 10 to the power minus 30 kilograms. Let me fix this. Upon fixing this, you'll know that I've actually done this calculation before. And the calculation is this. So it was this. So delta P is nothing but H by A. And we are taking the square of that. So that comes out to be 410 to the power minus 50. And in fact, I don't even need to keep the factor of 2 there. I can even bring the factor of 2 in. So the only thing that has increased is a factor of pi here. So it is pi squared by this. And I know this quantity, yes, uh, I know this quantity for these values is approximately 1 MeV. And you know what? Pi squared is 3.14. Square root of 10 is 3.16 something. So you know what? I will say pi squared is approximately 10, which implies E min, the ground state energy, is approximately 10 millielectron volts. And I told you a millielectron volt was a significant quantity. And turns out if I have a 5 nanometer box and I'm trying to confine an electron inside it, the actual minimum energy that we get by properly solving the Schrodinger equation is 10 times of what we estimated. And what was our estimate there? That is the absolute minimum possible energy. If we see, oh no, further, yeah, if we look at this problem, this is like the minimum energy that can be possessed by this. So we essentially said E is greater than this, and as we can see by solving, this is definitely greater than 1 MeV. So our estimate was actually not too bad. It was in fact pretty good. And this energy, the minimum energy a quantum system can hold, so the minimum, because in the classical world, what happens is we will say that yeah, a system can have that is not moving, that is completely still, is a zero energy system. The ground state, it is relaxed and it has zero energy. But that is not true in the quantum realm, quantum regime. So the minimum energy that can be possessed I'm not remembering the spelling of possessed. So I'm going to change my sentence and I'm going to say that a particle, a quantum particle, can have is called the 0 point energy. Essentially, energy now no longer has a zero level. This is the new zero level for this system. And there are systems where I can create a kind of a confinement potential where the energy actually reaches this minimum possible estimate. Those who already have studied some quantum mechanics know what that system is. Again, since we are not doing a quantum mechanics course, I am not going to say what it is, just to avoid, just to what to say, like prevent myself from distracting you too much, because we've already like near the end of the session, and I would like to cover the last topic also before we are done. And this is a very important consequence of quantum confinement. Whenever I'm confining a quantum system, it can no longer have zero energy. It needs to have a finite non-zero energy to exist in that system. And that is a direct consequence of the Heisenberg uncertainty principle. And that energy is referred to as the 0 point energy. Now you can ask, where does this energy come from? Like, let me assume initially the well was infinitely wide, and let us say a was tending to infinity. If a tends to infinity, we can see that of course this quantity will tend to 0 because as a tends to infinity, it is in the reciprocal. Uh, then I'm gradually bringing the walls together. Now, where is the particle getting the energy from? The answer is actually not too difficult to see. The point is when we are trying to bring the well, like make the size of the well smaller, like when I'm moving these infinite barriers closer and closer and closer, which is similar to reducing the size of this box. Not similar, it is exactly that process, identical to that process. We will be doing some work. What quantum mechanics tells us is that work that the external agent who's trying to confine a quantum particle is doing, some of it is transferred to the particle itself. And how much is transferred depends on how much work I do to confine. If I want to make the confinement even smaller, I need to supply more energy. If I want to make it further smaller, I need to supply it more energy. And the amount of energy I will be supplying will become more and more and more. And as A tends to 0, this energy will tend to infinity, which implies I can never make A tend to 0, meaning I can never confine a quantum particle at a single point because that confinement has an infinite energy cost. And this is at the very heart of the idea of quantum particles. I will try to discuss some more things, in the next week's session also. But due to the shortage of time, let us move to the final topic of the day, which is the Bloch's theorem. We're not going to do many problems here. I'm kind of setting this up as a prelude to the upcoming session on the Kronig-Penney theorem. I will kind of begin from here and move. I will just have one comment to make here before we end this session. So the wave function, like of course, now Bloch's theorem applies to a special kind of potential. Potentials of this form. V of x is equal to V of x plus L. What are these potentials called? These potentials are called periodic potentials. And Bloch's theorem tells me that if a potential is periodic, then the wave function has this form. Psi of x can be written as e to the power ikx times u of x, where u of x is equal to u of x plus L. Alternatively, one can write another statement, which is what many of you may have seen even in the slides. You will have seen this expression, psi of x plus L is equal to e to the power I k L times psi of x. Now, if you observe, these two are equivalent because if I put x equal to x plus L here, I will have e to the power I k x plus L plus u of x plus L. But since I've told u of x is already periodic, u of x plus L will become u of x. And e to the power ikx plus L is e to the power ikx into e to the power ikl. If I take the ikl common, I will have e to the power ikx into u of x, which is psi of x. So this is an alternate statement of the same theorem. These two statements are equivalent. Please look at what is on the right hand side. If it is u of x or psi of x, like essentially observe the equation carefully before answering any question related to it. So now what is so special about this solution and why this solution? So this actually relates to a very fundamental property of quantum mechanics. Now we know psi of x. Let us try to calculate what mod psi of x is. So what is mod psi of x? That is equal to mod e to the power ikx into mod u of x, because mod ab is mod a into mod b. Like this, that's a very common. That's a property of the modulus function. But I know this is 1, which implies mod psi of x is actually equal to mod ux. That further implies mod squared psi of x. The square of this modulus is equal to u of x squared. Now, since psi of x is now, what I can say is, this further implies, or rather, let me conclude by saying, therefore, mod squared psi of x plus L is equal to mod squared u of x plus L which is equal to mod squared ux. And this is essentially what the Bloch's theorem is trying to tell us. What this is trying to tell us is the following. In a periodic potential, the probability distribution function or density function. Wait, did I write it as distribution function before? Uh, oh no, I wrote it as density function. No, not oh no. Oh yes, I wrote it as probability density function. So yeah, the probability density function is also periodic. More generally, what I can say is the following. And this is also, just one second, I seem to have lost track of my, yeah, here it is. Since these dots are small, I need to like visually track them. Yeah. In general, now what I'm saying here is not particularly relevant for the course. This is kind of like, extra information because we are, winding up the session. Any symmetry of the potential is also present in the probability density function. Oops. Present in potential. So yeah, let me just do something here. Let me say b of x. Also present in mod psi of x squared, mod squared psi of x. So whatever symmetry my potential has, it can have reflection symmetry, it can have spherical symmetry, it can have, this is a case of translational symmetry, it can have some other rotational symmetry. Whatever symmetry the potential has, the magnitude square of the wave function will also have the same potential. And that can be proven using operator theory and things like that. Uh, for those who are interested, along with these slides, as supplementary material, I will add that. I would like to emphasize that that is completely unnecessary for the course, but those who are interested can go through that material and, just learn it for your own information. The proof of that is essentially at the heart of what is the quantum version of Noether's theorem. There is an equivalent, Emmy Noether was a German mathematician who worked on like a great many number of topics. Among that, she also derived a theorem in classical mechanics which talks about symmetries of a system and their properties, and that was readily extended. Like Noether's work was, around the same time as the founding of quantum mechanics. It was in the 1920s. So people at that time were able to migrate her theorem from the classical physics to quantum mechanics, classical mechanics to quantum mechanics. And the quantum version essentially gives us this property here. Like whatever symmetry my periodic potential has, the probability density function, mod squared psi of x, will also have the same thing. And Bloch's theorem is a particular instance of that generalized theorem. So from this, we will look at cases where we are solving the chronic penny model. So next week's session will begin from that. Uh, one more like final comment before the end of this session. Usually how the session will go is like I will solve some fixed number of problems during these sessions and discuss whatever was covered in the previous week so that it kind of helps with your assignment submissions. Additionally, I will also go through the course forums, see what questions are posted there, try to answer them there, and I will also address them during the sessions for the benefit of everyone. You can also, so whatever, if anybody has posted a question on the forum, you are free to join this session and have an in-person interaction. And any other questions that you may ask, I will also discuss it during the same session. And depending on what kind of questions are around, if needed, I will also be providing some supplementary materials, either material that I write or some other thing that I may refer to. I will kind of include it along with these slides. The slides and the link to the online version of this recording will both be made available to you through the NPTEL course announcements. You should have that by I don't know, as soon as I upload this session, you should have that information with you. So, with that, I thank you all for attending this session. And there were some technical difficulties before the session began. So, I apologize for any delays that may have caused, any inconvenience that may have caused. Rest assured, I will address those issues, and the future sessions will happen in a much more smooth manner. So, with that, I thank you all once again for attending. We shall meet again on the same time next week. I shall now stop the recording and end the call.